Hello and welcome to this tutorial. Today we'll be learning how to use SpaCy, a powerful natural language processing library, to integrate pre-trained embeddings into a deep learning pipeline. By the end of this video, you'll know how to leverage SpaCy's embeddings and use them effectively in a machine learning project. SpaCy is widely used in NLP for tasks like tokenization, lemmatization, named entity recognition, and dependency parsing. It's particularly well known for its speed and efficiency when handling large volumes of text data. What's exciting about SpaCy, however, is its ability to create word embeddings, which are fixed-size numerical vectors that capture semantic information about words. These embeddings are useful for tasks like text classification, sentiment analysis, and even more complex tasks like question answering. So why use pre-trained embeddings? Well, pre-trained embeddings save time and computational resources. Instead of training embeddings from scratch, which requires vast amounts of data and computational power, we use embeddings already trained on large texts. SpaCy models come with different sizes of embeddings, ranging from smaller, faster models to large, more precise ones. For example, here we download the N Core Web Small, Medium, and Large models. N stands for English, and SM, MD, and LG stands for Small, Medium, and Large. Here we also load the dataset, which is the IMDb dataset, and we use a dataset library to download it. And we join the train and test parts of the dataset, and we do the split ourselves, so we have more control over the data. And here we can also see that the dataset is balanced, so this corresponds to 30% of test labels and 70% of train labels. And here we load our SpaCy models. In this notebook, I've optimized the pipeline by disabling some of SpaCy's default features, such as dependency parsings and named entity recognition, to focus solely on embedding extraction, as this makes running the code much faster, as by default SpaCy turns everything on and tries to do everything all at once. So first we pre-process the data by extracting the vectors from the SpaCy object and taking the mean over all the tokens in a text. So we take the mean of all token vectors that have valid embeddings inside the text. So this averaging step ensures that overall semantic information of the text is captured in a fixed size vector. This is particularly useful because text can have a varying number of tokens, and by taking the mean, we condense all the tokens embeddings into a single consistent vector size, regardless of the input length, and each token contributes equally to the final representation, preventing any one token or another from dominating the result. So this method is efficient and works well for texts where the overall meaning of the text is more important than the exact sequence of words, such as text classification or sentiment analysis, which is our case. We're trying to determine if a single reveal has a positive reveal or is a negative reveal. Here we just prepare the data, so we take all the text and labels and run them over in the preprocess text function, and we then return all the embeddings and their corresponding labels. Here we define the dataset object, which is needed to work with PyTorch. So we define the embeddings attribute, the labels attribute, and all the respective methods that are required. Here we define our deep learning model. The sentiment classifier class defines a simple feed-forward neural network designed for binary sentiment classification. The model inherits from nn.module, which is PyTorch's base class for constructing neural networks. Its architecture consists of a single fully connected linear layer which maps the input features directly to a single output node. This output represents the raw score or logit for the positive sentiment class, and the forward method applies this layer to the input data and uses dot squeeze to reduce unnecessary dimensions, ensuring the output is a scalar value per sample. Here we define a simple function to train the model. So we receive the train loader, the train embeddings, and we define also the number of epochs. So we choose binary cross-entropy with logits for the loss function, and the Adam optimizer with a learning rate of 0.001. And here we use the epochs and train our model, observing the loss at each epoch. And here we also have a simple function to evaluate the model. So by passing the model and the test loader, we can calculate the test accuracy of a specific model. So first, let's try with the small model. We prepare the data with the train text and train labels, and also pass the NLP small model. We can also observe that the embeddings returned from the small model have 96 dimensions, so they are quite small actually. Then we initiate the data sets, the data loaders, and train our model. We can see that the losses are very big, so they go from 368 to 323. And after we evaluate our model, we have a test accuracy of only 0.66, so it's not that great actually. So by comparing with the medium pre-trained embeddings, we can see that by just replacing underscore SM with underscore MD, we can retrain the model with better embeddings. And we can also see that the embeddings dimension is 300 here, which is significantly greater than the small model. And after training it, we can see that the loss goes from 363 to all the way to 260, which gives us a test accuracy of 0.76. This is much better than the small model, but let's also take a look at the large model. Once again, we substitute underscore MD with underscore LG. And we can also see that the large model also has 300 embedding dimension. So it's not larger than the medium one. They both have the same embedding size. And after training it, we can also see that the loss goes from 351 all the way to 184, which gives us a test accuracy of 0.85, which is much better than the medium and large model, and small model, sorry. Here we have a quick summary of all the accuracies, and I hope that with this video you could save yourself some time and use pre-trained embeddings from a great library such as SpaCy. That way you can focus on tinkering with your deep learning pipeline, adding more layers, hidden layers, changing the input dimension and all the things that matter, and spend less time on training and evaluating embeddings, as the library abstracts that away from you. Well, I hope you will enjoy this tutorial, and this material will be available at the description. Any questions? I'll be happy to help you in the comments section. Thank you so much.